Hello. Sorry, I got disconnected. Can you hear me?
Yes, yes.
Okay. Sorry. Yeah, sorry about that. Okay. So let me just restart that. Okay, so my internet connection is not very great, so let me not switch on my video. Maybe it's using up the bandwidth. Okay, let's hope we don't have any more interruptions now. Okay, so like I was saying before we got cut off. So these are the two conditions that should be satisfied when we are talking about remainder and quotient in any calculation, right? Whether it's whichever is the positive value, whichever is a higher value, whether you have a decimal number is a quotient or not. I mean, yeah, whether the quotient is going to be z- around zero or whatever. So we'll take these two cases. So x and the simple x and y, x is 100, y is 3 that you can see here. And right, so if I calculate q1 and r1, right, so you can see here that q1 is 33, which is correct, right? 3 into 33, that's 99, and then remainder is 1, so that's right, 2. And just to see whether these are actually what we expected them to be, so q2 and r2 are also coming out to be the same value, right? So whether you're using this function to find the quotient or whether you're using floor, it's the same thing. Likewise, whether you are calculating the remainder using the remainder function or whether you're using an equation version, it's again the same thing. And we'll take one more example. So let's take this one. If I run this, so x is negative, and so the x is negative 3 and y is 100. So you can see that when you divide minus 3 by 100, right? So it's going to give you a decimal negative value, right? It's going to be 0.0 something. So an integer lower than that is going to be -1. And then you want that this condition should be satisfied. So this is going to be satisfied with 97. All right. So again, think about it. Take a look at this. So it's just that it's better to know, because like I mentioned, if you appear for the exam, you would not have access to R Studio, but you need to understand how R would have processed those statements, those commands, and then answer accordingly. All right. Okay. So that's the remaining bit from the last class. And now we'll start off with what we have for today. Okay, so last session we started talking about what are matrices and how you can define a matrix. So there are mainly 4 arguments that you need to give. And we talked that these are actually named arguments. So you can give a name for each of them. So these names are defined. So data, nrow, ncol, and byrow. These are the 4 arguments that are recognizes within the matrix function. So the plus point of having named arguments is that you don't need to remember which order they need to come in. You just mention that you can mention data and then you can mention ncol, nrow, and byrow after that, or in any order you can jumble them. However, if you instead of remembering names, if you want to remember the position in which these arguments came, that is also doable. But that's slightly tough, especially if you have more than 4 arguments, right? This may still be something that you can remember, that okay, data means the first argument is generally you give the value. The next 2 arguments we've talked about that generally always you mention number of rows or rows first, and then you talk about the columns. And then this one, the by row, that which order do you want to fill your matrix in? Should it be um, row wise, so the first row and then the second row and then the third row, or should it be column wise? All right. So we'll start off defining a matrix first. So again, I'm pressing Control Enter, and then we have our matrix defined here. So the information that you get here is that it's a number matrix or a numeric matrix. And within the square brackets, it indicates the dimensions. So it has two dimensions, right? It has rows and columns. So before the comma, you're talking about the rows. So we say it has 3 rows here, 1, 2, and 3, and it has 2 columns, 1 and 2. And that is what we had defined it as. And in our studio, you can also click on this. You can see that I have a hand made now instead of a normal cursor. So if I click on this, you can see this function gets executed here, view and that data. And this view has a capital V to it. So you can also just directly type view and your data name, and that opens up here. So here, this was filled row wise, right? Because by row was true. So it's filled in like this. And what you can see here is that each of the columns in each of the rows, they have some sort of names to them. Okay. Definitely there is a number. So there is row number and column number, right? Which is something you definitely understand, right? That is always in an ascending order, starting from 1. But row names and row numbers can be changed. Oh, sorry. Row names and column names can be changed. Okay. So we'll be using these functions, row names, and like we've been talking about, a word followed by a curved bracket is a function. So row names and call names, these are the functions. And you can use these functions to obtain the current names, obtain the current row names or the current column names. And you can also use these to define column names and row names. Okay, so what we can do here is let's check what the current row names and call names are. Okay, so if I run this, it says it does not have any row names right now. If I say call names, it says it does not have any call names. So this V1 and V2 that you see here, this is just like a placeholder. It's not its column name as such. And right now, and of course, these 1, 2, and 3 that you see, this is just numbers. Okay. Now what I can do is, so if I want to assign something, so think of this as a variable in itself. Think of this as a storage variable. So when I run this, it's going to give me what are the current values stored in them. So currently there was no value stored in it, so it gave me null. Now what I'll do is I'll store some values into it. So to store a value or to assign a value, this is what I'm going to write, right? So I have a vector because it's going to be more than 1. So because there are 3 rows, so I'll have a vector with 3 elements, and names are always going to be in double quotes, right? So I'm just calling them maybe gene 1, gene 10, gene 22, right? Any names, and then I'm going to assign it to row names of that matrix. Likewise, for column names also, I'm defining a vector which has just 2 elements to it. I'm calling it col1, col2, and then I'm going to assign it to the column names of M. Okay, so I'm going to run this. Okay, so it already, sometimes R does this, it executes it and it opens up those. But anyway, so what you can see here, what happened now is that instead of those 1, 2, 3 and V1, V2, it now shows up those names. Those numbers are still existent. Okay, you can always refer to the first row as the first row or the second column as the second column, right? So those positions are always there internally. But now you also have these names to it, call names and row names, right? So if I run the row names function again, it does not give me null anymore, right? It gave me null earlier, but now it doesn't give null values. It gives these values that we just assigned. Okay. Are we good till here? Yes. Okay. I'm assuming it's fine. Okay. Now, so here we've always been giving data in the form of a vector, and this vector always has elements as much as the number of elements that are going to be there in the matrix. But what if I just say, I give just one number as my data? So what's going to happen is that all the elements of that matrix are going to be that single number. So the same element. This could have also been a character element. So it would have been a character matrix. Okay. And so, all right. So now we can also have some matrix, something called a diagonal matrix. Okay. So now, uh, just like you have the matrix function, you can also have a function called diag or diag, however you want to pronounce it. And again, here also you have to give it the data. Now you can see here that I've not explicitly mentioned data is equal to, but because it's the first argument, I'm using it on the first position, so I don't explicitly need to mention, but I could have written data in here as well, right? But doesn't matter, anything's okay. So if I write this, and I'm writing 3 rows and 3 columns, and if I'm running this vector now, running this command now, so you see what happens here. I got a matrix, so it's a 3 by 3 matrix, and only the diagonal elements got filled with the numbers that I mentioned. Okay, now can you think what might happen if I'm doing this function, if I'm running line number 69 here, that diag 1 2 3, but it has 3 columns and 5 rows? What do you think is going to be there? So okay, it did not run with an error, or it did not give a warning, but how do you think the elements are going to be arranged? You can unmute yourselves, or you can type. Anything's okay.
1, 2, 3, then 1, 2.
Good point. Okay, so that's a very good thought process. However, if you try to make if you try to make a matrix which has these dimensions, okay, then what you're going to see is it actually does not have 5 diagonals to begin with. So how do we define a diagonal, or how do we define a diagonal element? Elements which have the same row and column positions. So 1 1 2 2 3 3 4 4 5 5 and so on. Right? Now you see this matrix. This is the element at 1 1. This is the element at 2 2. This is the element at 3 3. There is no 4 4 element here, or there's no 5 5 element. Right? So which is why it just has three diagonal elements, and so it fills in 1 2 3. But the point that you mentioned, okay, so what we can try here, okay, let's call this, and let's call it G here. So I'm not using the variable name as F, because that's reserved for false, right? You remember? So you remember, if I type F, you can see it's already coming up in a different color, because it R recognizes F as a reserved variable. So now if I would have okay, so if I would run something like this, right? Then this is what's happening, what you mentioned, that it has 3 diagonal elements, but I only gave it 2 out of those 3. So instead of the third, like instead of not putting anything in the third position, is going to recycle that same vector, right? So that's what's happening. So very good answer.
Ma'am, I am
Yes.
just like if we change like a number of column is greater than number of row, I think same will happen.
Yes, same thing will happen. So let's try another thing. I'm just putting them in order, so I'm changing the name of the variable. So let's say if we do the same thing, let's say n call is 5 and n row is 3. Now even then you can see that there will still be 3 diagonal elements, right?
Yes.
It's just that now they look a little different. The it's a long, it's a horizontal matrix, so as to say, rather than a vertical longer one, right? But it's still the same thing.
All.
Okay. All right. Perfect. So, so yes, so this is what we said, that a diagonal matrix is also possible. So this is what we uh, just did. And again, like in the previous case, if you just give it one element, so it's just going to recycle that element across all possible places. So again, those rules that you've seen in the past, they are all extrapolated here, right? So you can have diagonal with different elements, you can have diagonal with the same element, anything's okay. Uh, Now we talk throughout in the next 10-15 minutes, we'll talk a few different matrix calculations and different um, types of matrices that you can make in terms of wherever matrix is used for calculations. So there's something called transpose of a matrix. So let's first see what our M looks like right now. So M currently has 2 columns and 3 rows, right? And like we've mentioned before, we always talk about row numbers first. So it's a 3 rows and 2 columns. So we'll say it's a 3 by 2 matrix. Okay, so we can put a comment here that it's a 3 by 2 matrix. Now, if you want to find something which is called a transpose, and transpose means we are swapping rows and columns. So the function here is T, just a single alphabet T, just like the combined function is C. So transpose is T and T, and inside you are writing the matrix. So if I'm saving that in N, so now I can see what happened here was. So yes, so now the rows have become columns, the columns have become rows, and the row names and column names have also swapped places. Okay, so just to double check that, let's see, we have row names and we have column names here. So you can see row names are now call 1, call 2, and call names are now gene 1, gene 10, gene 22. Okay, so that's, we will see where all transpose comes into play. But transpose very often, so sometimes when you'll be making some, maybe some more complicated commands and using matrices to do some calculations, sometimes these functions, they would require you, let's say, to have particular values as rows rather than columns. But let's say when you were saving data, you did it the other way. So you just want to swap it, right? But, and also those of you who might have used Excel a little more extensively, you would have used transpose in Excel. So it's pretty much the same thing. Okay. Now, especially when you have number matrices or numeric matrices, which is where matrices are most commonly used, um, you can find sum of each column, you can find sum of each row. And since you have found sum, you can also find means, which is the average of each row and each column, right? So the nomenclature has to be a little, you have to be a little careful with what you're doing. It can be a little bit confusing sometimes. Okay, so when we are saying row sums, okay, so it means you are finding the sum of each row, right? So we'll be taking M as the example for most of our things here. So in M, can you tell me, if if I do this calculation, row sums, what output am I going to get? And so what is going to be the type of the output? Is it going to be a single value? Is it going to be multiple values? What do we call such values? And what would those values be? So how many values and
Suppose,
what value? Sorry.
I mean 3, 7, 11. It's a one row, one column.
Perfect. Okay. That is correct. Now, instead of calling it a column, we'll call it a vector. Okay. So it's right to think that this, let's say, gives you a sum here. This gives you a sum somewhere here. This gives you a sum again here. So it is equivalent to another column, but the dimensions, the way if you save it, it's going to emerge like a vector. Okay, we've been seeing vectors so far, right? So like this. So this is a vector. Now, what you might see here is that you also get the row names associated with each sum. So it's a named vector. Okay. So it returns a named vector. We'll go into it a bit later. It's not absolutely essential right now, but just remember that it is a vector. It is multiple values one after the other, right? And likewise, we'll have call sums. So it's going to be sum of each column. So that's going to be 9 and then 12. Okay, for each of the columns. And again, you can also find if you found the sum, you can also find the mean. So it's going to be row means and call means. Again, just remember that R is case sensitive. So very often you have these capital alphabets here and there. So that's important to remember. So again, once you calculate that, yeah, so it's so when you're doing the mean, so it's again the simple yeah, so it's like this. Where do we have? Okay, so this is going to be your, so if we are doing this average of a row, so you're dividing it by the number of columns, right? You're summing up the row and you're dividing it by the number of columns. So you're dividing, so 1 plus 2 divided by 2, 3 plus 4 divided by 2, 5 plus 6 divided by 2. And for call means you are summing up the column and dividing by the number of rows. So that's going to be 9 by 3 and then 12 by 3, right? So again, just what we wrote here, that row means is basically your row sums divided by the number of columns. Again, this is just to improve your understanding. It can look a bit complicated, but the more you the more you try to type all of this yourself, you'll get more familiar with these notations. Okay, now I have a question for you here, and there are multiple correct answers. So again, we have this matrix M for your reference here. If I want to find the sum of the second row, so basically this value, I want to add 3 and 4 here. There could be multiple correct answers. Again, each of them is equally correct. It's upon you what you like the most, what comes up in your mind first. But how do you think I would find the find the sum of a particular row? If I want to find the sum of second row, what do I type?
I'm not sure, but yeah, a row sum m,
Hmm.
comma, in n row equal to 2.
Say that again.
Row sum m,
Yeah, this I've written. Okay.
and in the same bracket,
Huh.
n row equal to 2.
Okay. Okay. So n row means number of rows, not the row position. So n row is, so whenever I'm writing n row in M, it gives me 3. So that's how many rows are there, total number. But you are kind of there. So, okay. Would you like to try again, or would anybody else like to give it a try? You'll see there are 3 or 4 correct answers I've written below this question. You can just shoot your answers. We'll see how to.
Some Priyam square bracket 2 comma
Sorry, I
जैसे
did not hear the first thing you said. Say that again.
some
हाँ.
फिर कैपिटल M
कौन सा ब्रैकेट?
स्क्वायर ब्रैकेट
स्क्वायर
मैम
ब्रैकेट,
स्मॉल ब्रैकेट फिर
कर्व
कैपिटल
ब्रैकेट.
M
हम्म.
फिर स्क्वायर ब्रैकेट
हम्म.
2 फिर कॉमास
Very good. That's correct. Good, good, perfect. So what have we done here is So remember, we'll start, whenever we are understanding this, we'll start off from the very inside of the bracket. So here we have taken just the second row of our matrix, and we are saying sum that thing. So we have only taken this and we are saying sum it up. So we're not using row sums here. So that's definitely one way.
Uh, we
Yes,
can specify the range of columns, right? With the
we
row.
can. Yes. So when we are doing, that's correct. So what this indicates is that we have taken all columns, right? When we don't mention columns. So before the comma, we are writing what row or rows we are interested in. And after the comma, we are writing what columns we are interested in. And if you have not written anything, we means we're talking about everything. Is that what you wanted to know?
Yeah.
Okay. All right. Yes. So to write it explicitly, we can write something like this, right? But there's no need. We don't need to write that.
It helps if we have to find the sums of particular columns.
Perfect. Yes, yes, yes. So let's say if you have 10 columns and you only want to find the sum of the 5th row and the 6th to 10th column, then yes, correct. Okay. So that's definitely one right way of calculating the sum of the second row. So any more tries, or should I give you the answers? Okay. If we don't have any more tries, then this is definitely what one of you mentioned. And so we just talked about this argument, this function here, right? So just like what we did earlier, if I save this into a vector D, and if I take a look at the vector D, so it's a normal vector. It just says it's named because it has these names associated, but don't get confused by that. Think of it as a simple 3-element vector. Now, out of these 3 elements, we want to pick the second element because we wanted to find the sum of the second row. So we want to pick the second element. And how do we pick a second element from anything, from a vector? We write the vector and we write that element position inside square brackets. So we can write that and we get 7. Likewise, if you want to combine these two steps, we can just write row sums, which is this thing here. And after that, we put a square bracket and put 2, because this is that vector D. Okay, it's the same thing as vector D. And from that vector, we want to extract the second position only. So that gives us the same answer as well. Okay, 7. And so this one's pretty much one answer. This is one more answer. And then this, again, this is a complicated thing, but you're explicitly adding up each of your elements in the second row. So that's going to be second row, first element, second row, second element. Each are of your matrix M, and then you're summing that up, right? Because this thing gives you 3, this thing gives you 4, and the sum, that's like a simple proper addition, gives you 7. Okay, so definitely this one and this one, they are the most straightforward ones. This is just extra, but nobody can say that it is an incorrect calculation. Okay, all right. So that's I think that was what was covered in lecture 13. Now in lecture 14, again we'll be talking a bit more about some more calculations that we can do with matrices. Again, we'll be focusing on numeric matrices. So what we just talked about as a dimension, that we always talk about rows and then columns. So if you write dim of any matrix, then it gives you a vector again, and the vector has 2 elements. And the first element is going to be number of rows, second element is going to be number of columns. Okay, and when you want to access either one element or multiple elements, from a matrix or from a vector, we always do it in square brackets. Now, depending on how many values you want, the shape of your output can be different. So if you explicitly mention one particular row and one particular column, you get an element, right? So this is going to give me the third rows and the second column element. Okay. So can you tell me what is that? What would line 116 give me?
6.
6. Perfect. Okay. And this is giving me a vector. So it's giving me, what vector is it going to give me?
3, 4.
3 and 4, because that's giving me the second row. Okay. And then this one is where I have more than one row and more than one column, right? So here I have second and third column, and I also have, sorry, I have the second and third row and the first and the second column. Okay. Maybe, do you think this would be correct as well? What does this mean?
The
What row?
first and third row.
First and third
And
row?
yeah, and both the columns.
Both the columns. Perfect. Okay, good. So just remember square brackets, and there's going to be a comma. There's going to be just one comma. Before that, you have to write a vector. After that, also you have like a single value or a vector, and after that also a single value or a vector. So here, this is how I've chosen to write a vector, because I had non-consecutive elements. And here, since I have consecutive elements, I can just write using a colon. All right, perfect. So this is almost as complicated as it can get. So if you've understood this, then we are progressing quite well. And if not, you just need a little more practice and you will get there. Okay, now,
Ma'am, can you repeat it once more?
okay. So let's take a look at, so this is the matrix M, right? We have 3 rows and 2 columns in this. And here when you are, so whenever you want to access one or more elements from a matrix, you always write the required positions inside a square bracket. And for a matrix, when you have 2 dimensions that you're working with, a row and a column, within the square bracket, so it's going to be like this. So you have the name of the matrix, you have the square bracket, and you put a comma. Anything you put before the comma corresponds to rows. Anything you put after the comma corresponds to columns. So in this case, I have put 3 as my row number and 2 as my column number. So my row number 3 and column number 2 has the element 6. So if I run this line, I'm going to get the output 6. Now in this case, I have mentioned second row, but I did not mention which column. So by default, it gives me all the columns. So that's 3 and 4. So that's going to give me a vector. In this case, it's a named vector, but doesn't matter. It's a vector. Were you saying something? No.
No. Yes,
All right.
thank you, ma'am.
Okay. And yeah, just to complete this, in this case, we're talking about first and third row, and we are talking about first and second column. So it's going to give me a mini matrix. I mean, it's a matrix. It's just a smaller version of the previous matrix. All right. Okay.
Yes, ma'am.
Now, about, just like we did some mathematical operations with matrix and with vectors, we can also do some of those with a matrix. Now, addition and multiplication. Okay, so what we are doing here is matrix with a scalar, and scalar means a single value. So when you're doing 2 plus m or m plus 2, both of them mean that you're adding the value 2 into each of your elements, right? So if this was m, then 2 plus m is going to be all elements have 2 added to them. But m plus 2 is also going to give you the same thing, right? Because addition is commutative. Likewise, if you do multiplication, then multiplication will also be okay. Whether you multiply matrix with 3 or you multiply 3 with the matrix, it's still the same thing. But for division and subtraction, definitely the order is important, right? So if I'm doing 10 minus m, I get this as the output because 10 minus each number one by one. And m minus 10 is a lot different, right? Because each number minus 10. Okay. So likewise with division. But it's going to be, so it's basically what you're doing is, it's the same multiplication or division, but with multiple elements. And this is what we have done with vectors as well. Now, when we are doing addition and subtraction of a matrix with another matrix, okay? So now think about it. This is going to be done element wise, okay? First row, first column with the first row, first column of the other matrix. First row, second column, and first row, second column of the other matrix, and so on, right? So now the order or the dimensions, should be the same for the two matrices that you're doing, right? So we have this M here, right, which has 3 rows and 2 columns. And we are defining one more matrix. Let's call it M2. And that also has, sorry. Yeah. So that also has 3 rows and 2 columns. Okay. So these have the same dimensions, 3 into 2. So if I add these up, right, you get the correct output. And you can see here that irrespective of what I'm doing, it's just taking up the names of the matrix where the names are present. But again, that's not super important. Basically, what we are doing here is adding up these matrices element wise. So you start off with the 3 by 2 matrix. You start off with 2 such matrices and you end up with 1 matrix of the same dimension. When you're doing subtraction, again, you need to have matrices in the same that have the same dimensions, but this is no longer commutative. And again, this is something you know, right? So m minus m2 is giving you a different answer, and m2 minus m is going to give you a different answer. Okay. Okay. Right. And likewise, so it's the same thing. Yeah. So it's not multiplication, it's whatever operator. Okay. And of course, you can also do multiplication here. So m multiplied by m2, m2 multiplied by m, right? So again, it's the same thing. This is going to be commutative, but when you do division, that is not going to be commutative. It's going to give you different answers. But the important aspect here is that the order or the dimensions of these matrices should be the same. So if you take a, let's call it, yeah, it doesn't matter, m by n, whatever it is, it should be consistent. Okay. Now we come to a slightly more complicated thing. So this is matrix multiplication, where we are not doing an element-wise multiplication, but rather we are multiplying matrices in a very mathematical sense. Now here what you need to remember. So let me quickly show you something here. Okay. So we take a very simple example here. Let me connect this. Okay. Pen moves here. All right. So Now here we have two matrices. This one, both of them here have a 2 by 2 dimensions. Now, the way we write the dimensions of a, so maybe some of you are already familiar with it from maths, but it's good to have a revision here. So whenever you're doing a matrix multiplication, you write it like this, that m by n multiplied by, let's say it's n by p. And then the output that you get is going to be m by p. Okay. For example, if you have a 2 by 3 matrix and you multiply that with a, let's say, a 3 by 4 matrix, then the output you get is a 2 by 4 matrix. Okay. Again, the more rows or the more columns we have, the more complicated it is to manually do that. But still, this can very much be done manually. The way you want to do it is, first of all, once you're clear with this setup, what you can try and do is, so let's take this example first. So you have these two matrices you want to multiply. Let's say we first want to do AB. So A into B. Now the first element here comes from the first row and the first column. So you do A into W plus B into Y. And then, okay. And then you get this value, right? Likewise, when you want to get the second, so it's the first row, second column. So again, first row, second column, and this one. Then for the second row, first column of your output, you take the second row and first column from your inputs. And what color can we use? Maybe this one. And for the second row, second column of your output, you take the second row, second column of your output. And if instead it was B into A, this becomes your second matrix and this becomes your first matrix. So you do a W into X and A into C, something like that. And the same thing gets extrapolated when you have more complicated matrices. But what you need to remember is that, first of all, matrix multiplication is not commutative, right? So A into B and B into A gives you different outputs. And the second thing that you need to remember is this condition should be satisfied. So since we started with a 2 by 2 matrix, you could actually do both calculations, A into B and B into A. But even if you're able to do it, it's not going to give you the same answer necessarily. Okay? If this is clear, then we can just check how you can do it very simply in R. Okay? So this is what we just saw. And the symbol that you have to use is this, %, asterisk, %. Okay? Now, so again, this is some very similar example that we have seen right now. So M, we have seen it's a 3 by 2 matrix. And we're defining another matrix called M3, and that is a 2 by 4 matrix. Okay, so can you tell me, should I do M into M3 or should I do M3 into M? Or can I do both?
We can do M into M3.
Yes, okay. Because 3 into 2. So the columns of the first matrix and the rows of the second matrix, that number should be same. So number of columns and number of rows. So yes, number of columns, number of rows here, right? And the dimension is going to be this and this, the remaining two numbers. So M multiplied by M3, that gives us an output. And if we have this one instead, it will not give us an output. So let's try running both of them. So this one, it gives an output of a 3 by 4 dimension. And if I do this one, it says error, non-conformable arguments, because whatever. It's something that it's not allowed. Okay. Now, you can also multiply a matrix with its transpose, and that can be done in both ways. So, for example, if you have a 3 by 2 matrix and the transpose is going to have the opposite dimension, it's going to be 2 by 3. Now, you can do both of them. So, this one also you can do, because these two numbers are the same. The output is going to be a 3 by 3 matrix. And if you do this one, then the output is going to be a 2 by 2 matrix. So again, multiplying a matrix with this transpose, it's allowed both ways, but again, the answers are going to be different in both cases, right? They're two very, very different matrices. Okay, we have this annotation thing on. Wait. Anyway, let it be. Wait. Okay. Okay. All right. Now there's just one more function that you can use. It's called the cross prod or the cross product. And if you just write the matrix there, then it's going to give you the second output. So transpose of the matrix multiplied by the matrix. So it gives you that. It's just an extra note. Okay. So yes, so that's about matrix multiplication. Now, very often you might want to combine matrices, in the sense you're not adding or subtracting or that, but you just want to place them next to each other, right? Now you can place them side by side, as in you have one matrix and then you place another matrix. I think I can draw this here. So let me make a new slide here. Okay. So if you have, let's say, two matrices, let's say we talk about three matrices here, and I'll give it random dimensions: 2 into 3, 3 into 2, and 3 into 3. Okay, so can you tell me, if I want to place two matrices like this, or if I want to place two matrices like this, which ones can be done this way? So let's take all cases. Can red and blue be placed next to each other like this?
Yes, it can be.
Yes. Okay. Let's see how that may be possible. So, okay. So if I have a 2 by 3 matrix, it means I have, so it's basically like this. This is the matrix. And here, this is the matrix. Right? Now, this one basically means it's going to be like this. This one's going to be like this. You can't place matrices like this. You cannot have empty elements somewhere, right? So you're going to have empty places here. So that you can't do. Okay. So, So yes, so red and blue cannot be placed side by side. Can red and green be placed side by side?
No, ma'am.
No. Okay. Can blue and green be placed side by side?
Yes.
Yes. Okay. So,
Yes.
all right, perfect. So if I have this blue matrix here, so it's going to look like this. And if I have this green matrix next to it, so I can do that. And if the total thing, I mean, it could be done in the other way also. So the only thing is if I have a 2 into 3 and 3 by 3 matrix, the final thing here, it's going to, it is, oh, sorry. Yeah, 3 by 2 and 3 by 3. So now I'm going to have a 3 by 5 matrix. I have 3 rows and 5 columns now. I could have done it the other way also. I could have my green matrix first, and then I can place the blue matrix after it. That would also be a 3 by 5 matrix, but it's going to look different. I have different rows and different columns in that order, but both of them are doable, right? So what we're doing here, we'll call it, this is called C bind. You're binding columns, column with column. So here, the number of rows was an important thing. Okay. So again, it can become very complicated if I keep referring to number of rows, number of columns. So you can always try and draw it out, and then you can see if it makes sense to combine them in that order. Okay. Likewise, quickly, can you think about which ones here can I combine one below the other? Red and blue, red and green, blue and green.
Red and green.
Red and green.
Red and green, right? The
Red
first and the
and
third
green.
one. Yes. Right? So again, it can be like this, followed by these 3. So 2 by 3 matrix and a 3 by 3, or it could be the other way also. And I'm sorry. Something like this. Right? So it's going to be a single matrix now. And what would be the dimensions of this new matrix?
5 by 3 matrix.
5 by 3. Perfect. Okay, great. So, yeah, so this one is going to be called R bind. So it's basically, you can remember it as C bind means placing columns next to columns, and R bind means placing rows below rows. Okay. Again, how you remember, that's up to you. It took me a very long time to get clear with what's what. I still mess up, but that's what comes with practice. Okay, so this is where we were. So yeah, when you're placing row below, so this is the first example that we took here. Let me just write it in the same order that we did. Okay, so column next to column, left and right. So number of rows has to be the same. And when you're placing rows below rows, right, when you're placing rows below rows, then the number of columns has to be the same. So we'll take examples. Again, this is pretty much what we just saw here. So I think I've redefined these 3 matrices. Okay, so M, what we've been talking, M2 is a smaller matrix, M3 is a larger matrix. Yeah, it's roughly what we've just discussed. So we can bind M and M3 left to right because they have the same number of rows, right? So it gives you a bigger matrix, which has 5 columns. And okay, yeah. And the other thing also you can do. Okay. Now, see this. what do you think is going to be, what do you think is happening here? One of you mentioned this a little time back, so it's kind of on those lines. What's happening in line number 197?
A matrix M bind with the vectors of sum of row.
Yes,
Like,
perfect. Yes, absolutely correct. So like one of you had mentioned that when we are doing sum of the rows, that vector is pretty much like a column, right? You can almost imagine that this output, this output, this output can be like a different column here. So it's exactly what we are doing when we are binding that. So the C bind and R bind, this does not only have to be done matrix with matrix. You can also do it matrix to a vector. It's just that you need to ensure. So for example, here, if let's say here, if we have, so let's say here, if it was this case, and we want to add one column to it, what you want to ensure is that this column should have the same number of elements as the rows in this matrix, right? So 3. Each column should have the same number of rows. Each row should have the same number of columns. That's the funda, right? So here we can add a vector which has 3 elements. 3 elements means number of rows. And that's what we got when we were calculating row sums also. So what we got here was, so this last column is actually sum of the previous 2 columns. Each of the rows, I mean, right? And the other way, you can also do R bind when you're talking about call sums. So it's like this. So 1, 3, and 5 give you 9, 2, 4, and 6 give you 12. And here I've just explicitly mentioned what the row sum is, but you could also do just any random vector, right? You can just put any vector that you want as a new column. So C bind and R bind can be used to add a new column or a new row to a matrix, respectively.
Ma'am, if we are doing 198 with the row bind, I think it will be error, right?
Yes, that's correct. So I meant row bind with call sums, but yeah.
Yes.
So if you're doing R bind of matrix with, let's say, this statement, then it's will go. So it is okay. So it did give you an answer,
Yeah, it's
but
like
yeah.
a default.
Yes. So the third element does not have any space.
Yeah.
So it just gave you a warning. Okay, but yes, good observation. Okay. And okay, so we will talk a little bit more about one more thing here. So there is something specifically, so okay, so let's see how we can understand this. So so basic algebra, if you have something like this written, okay, if you want to calculate the value of x, what you're going to do is that you'll take this a here. So basically it's b upon a. You might also want to write it as b into a to the power minus 1, right? Minus 1 pretty much means you're taking a 1 upon that. Now, when you're talking about matrices, there is something a little bit similar that you can do. So let's say here also, if I just have, so very often capital letters are used to denote matrices. Now, if I actually want to do the same thing, now remember, if you think of A as a matrix, we can write this thing here, right? A minus 1, a to the power minus 1. So that is actually the inverse of a matrix. And it's not as straightforward as 1 upon that matrix. It's slightly more complicated. But it's you can calculate it. It's doable. It's very doable manually with for 2 by 2 matrix, but we're not going to go into that right now. There is something called a determinant of a matrix, which is for a 2 by 2 matrix, it is A into D minus B into C. Basically this and this element like that. If it is non-zero, matrix inverse can be calculated. So determinant should be non-zero, or a better way to write that is det of A is not equal to 0. If this condition is satisfied, then you can calculate the inverse. And again, there is a simple command in R to calculate the inverse, and that's simply solve A. That's it. That's the command. And we'll come back to the slide in another few minutes. There's one more thing that I want to discuss. But yeah, so inverse of a matrix. And so yes, so inverse is only defined for square matrices, and the determinant of that square matrix should be non-zero. So so if I define a new matrix N here, okay, yes, so if I define this matrix and if I write solve for N, it gives you another matrix of the same dimensions, and that's your inverse of N, right? Now, we can also do that for a larger matrix, for a 3 by 3 matrix. And okay, I think there's something in this matrix why it's not it's not able to calculate it. Must be something. Anyway, but the thing is that using the solve function, you can calculate the inverse of a matrix. Okay.
मैम डिटर्मिनेंट के लिए क्या करेंगे?
Sorry, say that again.
एडजॉइंट और डिटर्मिनेंट, मैम डिटर्मिनेंट और एडजॉइंट के लिए कौन सा फंक्शन यूज करेंगे?
Your voice is not clear.
मैम डिटर्मिनेंट और एडजॉइंट अगर निकालना हो मैट्रिक्स का तो फिर कौन सा फंक्शन यूज करेंगे?
Oh, determinant and adjoint. Let's see. Yeah, det is a function. So, okay. So, function det, det. So, I think det of M3 this is almost 0. It's a very small value, right? E to the power minus 16. So, I think this is almost 0. So, which is why, since the determinant of M3 is 0, so it was not able to calculate the inverse of that matrix. So yes, you can do determinant of N. Let's do it this way. And then you can also do determinant of M3. This is almost 0. So this is why you cannot be calculated. Okay. All right. Then what we just saw, okay, so when we were doing these matrix multiplications, right? Yes.
और एडजॉइंट एडिंग
Oh, adjoint, I am not sure. I will have to check. I have actually forgotten what adjoint is. I'm hearing this word after a very long time. Okay, let me check and I'll let you know in the next class. Okay, but meanwhile, if you are able to find that, you can post it in the discussion forum of the course, just for everybody to know. Okay?
Yeah.
All right. So here we were talking about this matrix multiplication, right? Now we can also do that with a vector. Again, the important part about multiplication that you want to take into account is that this should be satisfied. Now, if you're talking about vector here, so suppose you have which is like a m by n matrix, and then if you have a vector which is an n by 1 vector, right? Then you can calculate it, your output, whatever the new matrix is, that's the new vector that's going to have this dimension, right? Let's say it's W. On the other hand, if you begin with a vector S, let's say, which has 1 into n as your dimensions, let's say 1 into m, and then you multiply it with a different matrix which has n, sorry, m into n itself, and then you'll get a different vector, let's say p, and that is going to have the dimensions this. So remember, we touched upon this briefly today sometime in the discussion, that a vector cannot exactly be called a column vector or a row vector. It is just an order of elements, but it can be used in either way. So that's a plus point. So a vector, so it's pretty much these two vectors. It's the same vector. It's a vector with m elements. One can be arranged in the form of a row, so which is this one. One can be arranged in the form of a column, which is this one. And you can do a matrix into vector multiplication, and you will get a vector as the output. It's just depending on how you calculated what was the order, whether it was a vector before a matrix or a matrix before a vector. But anyway, both of these things are doable. Okay, so for example, if this was your matrix, the matrix M that we've been, the matrix M that we've been talking about, and we have this vector 3, 4, this one. Now you can consider it as a 1 by 2 vector or a 2 by 1 vector. That is okay. But now if you want to multiply these two, then this case is only possible for multiplication, right? So M into V. So if you want to do that, then we can do this one. And then we got the output as a 3 into 1 vector. It's in the form of a matrix right now, but still it's a 3 by 1 output. Does this make sense? I hope I did not confuse you very much. Tell me if the selected region, if this makes sense.
मैम ये एलिमेंट वाइज हो रहा है या फिर वो मैट्रिक्स जो
Matrix वाला ही हो रहा है. So let's take the example. Okay. So maybe I will draw this 1, 2, 3, 4, 5, 6, है ना? Okay. So let's make a new slide here, and let's remove this. Okay. So here we had a 1, 2, 3, 4, 5, 6 matrix, and we had 3, 4 as a vector, right? So this is a 3 by 2 matrix, and this can be considered as a 1 by 2 vector also, as a 2 by 1 vector also, anything. Now, if you want to multiply this and this, then this is the only form in which it can be multiplied. So we'll call it a 2 by 1 matrix. So 2 by 1 means 2 by 1 vector, 2 by 1 matrix in this case. So it means it's going to look like this: 2 rows and 2 rows and 1 column. And then the output that we get, that's going to be of the dimensions 3 by 1, like this. So what we are going to do here is, so I'll go over this a little quickly because it's not the main aspect of the course, but it's going to be 1 into 3 plus 2 into 4, that's 8 for the first element. Then 3 into 3 plus 4 into 4 for the second element. And 5 into 3 plus 6 into 4 for the third element. So that's 11, 25, and 39. Okay, and I hope this is what we got there. Yes, right? So it's the same, proper matrix multiplication, not element wise. Element wise is only possible when you have the exact
Okay.
same dimensions, right? Okay. All right. Now, one final thing for the matrix thing. Let me again make a new slide here. Okay, so we just talked about this vector example, right? So, so for example, we have a vector and we have a matrix. Now, if I say, if it was a square matrix, right? So if it was a M into M matrix, and if this vector is a 1 into M vector, then you can multiply them, right? And the way we are going to multiply it is and whatever the output we get, let's say it's a vector W, that would have the form 1 into M, right? I hope this thing is clear. So 1 into M and M into M can be multiplied by the rule we just saw, and the output is going to be 1 by M. Now you see the the dimensions of the input vector and the output vector is the same. So in some cases, so this is okay, but now what happens in some cases, this calculation can give you the original vector back multiplied by a certain scalar number. Okay, we'll take some example, but let's say if what you fed was 2 into 3, okay, and then here you had some 2 by 2 matrix, and then the output you got, let's say, was 4 comma 6. Now you can write 4 comma 6 as 2 into 2 comma 3, right? Yes, this if you get something like this as an output, what you can say is that for this matrix M, 2 comma 3 is its eigenvector and 2 is the corresponding eigenvalue. That's how you say it. Now, I will not be going into what is eigenvector and eigenvalue. That's very complicated. I myself don't understand that 100%. But the thing is that not all matrices will have an eigenvector and eigenvalue. It's only some square matrices can have that. Okay. So first condition definitely is it has to be a square matrix, but also not all square matrices will have that. Okay. But if you do want to find, what its possible vector is, so we can take the example of our n square matrix here. The way you can calculate that is the function eigen. So if I calculate just eigen here, you see it gives me, it says it's eigen decomposition. That's how it's called in maths. It returns me two sets of outputs. So typically we've always seen it's been one output, right? Now you see here, it gave me two outputs. It's a list. We have not yet talked about lists. We'll talk about it a bit later. But it's basically there are two sets of outputs. The first set, which you can access by the symbol dollar, that's E. So the E is where we saved the output, right? So E dollar values. And the second set is called vectors. So we can access it through E dollar vectors. This dollar symbol is going to come a lot more now. Dollar symbol is always used to access a named component of a structure. So think about it here. The structure we're talking about here is a list. And there are two named components in that. The first named component is values. The second named component is vectors. Okay, so we want to access that. So we'll say E dollar values, E dollar vectors. So for this N matrix, -2, 1 was a, -2 and 1 are eigenvectors, eigenvalues. So it has two eigenvalues. Yes, so sorry, one more thing. Number of eigenvectors or eigenvalues will be equal to the dimension of that matrix. So if it's M, you're going to have two vectors and two values, if at all you have something. So here, this is the first one. So the first vector, that's the column vector here. So 0.948 and 0.316, that's the first vector. And 0 and 1 is the second vector. So let's, just for the sake of completion, let's try this. Okay, I think I can do it this way. Okay, please confirm if you can. No, it's not gonna work. Okay, let it be. We'll do it the usual way. So the n vector here was -2, 0, -1, 1. Okay. So in our example, it was -2, 0, -1, 1. And one of the eigenvectors was 0, 1. Okay. So 0, 1. Now, if we multiply these, so this is 0. Sorry, not like this. We're going to write it like this. Yes. So 0 plus -1 and 0 plus -1. What am I doing wrong? Give me 1 second. I might be doing something wrong here. Anyway, let me get back to you on this next time. It's not super important. It was just to make it clearer, but it's better I don't confuse you. Okay, so if we get time at the end, we'll come back to this. But the main thing you need to remember is there's something called eigenvector and eigenvalue, and this is how you will calculate that in R. Okay, now the last thing that was covered was something about the logical and the relational operators. So we have used these operators for now, right? It's just that the ones we're talking about now look a little similar. So this is the assignment operator, and this is also the single is equal to is also used as an assignment, right? Now you're familiar with the less than symbol, the greater than symbol. Yeah, let's say it's this one. So it's less than equal to, greater than equal to. And if you want to compare two numbers, whether they are equal or not, then you have to use 2 is equal to at a time, right? Double is equal to is for comparison. And then you can also do something like a not equal to. So it's going to be exclamation into, like exclamation followed by an is equal to symbol. Okay, so we have x defined here. Let's say we have x defined as -3 for now. So we're not running these, or yeah, maybe we can run this. So x is 20. Now x less than 40. So this output is going to be true or false. So either you can write true all the letters in capital, or you just write capital T. Likewise, you write false all the capital letters, or just F. R will understand both of them. But when it's giving an output, it's usually going to give you all output, the entire word. So x less than 40, that's going to give you false. Sorry, that's going to give you true, right? That's 20. X greater than 10, that's also going to give you true. X less than equal to 20, that's true as well. Okay, let me change some numbers here. Yeah. X greater than equal to 30, that will give us false. X is equal to 20, that's true. X is equal to 5, that's not true. X is not equal to 5, that is true. But x is not equal to 20, that is false. Okay, so this is when we are doing a single comparison. You can also do multiple comparisons, right? Which look something like this. Is x, so maybe what makes sense is something like this. So is x greater than, is x less than 15 and greater than 5? That means we are looking at x between 5 and 15, right? So this AND symbol, so this AND symbol is telling us if only both conditions are satisfied. If this is also satisfied and if this is also satisfied, then give us true. So you can take a look at this table here. So typically we'll do two comparisons at a time. So if both of them are true, then AND gives us true. But if one of them is true only, or if both of them are false, then AND gives us false. You might have read this, or you might have come across this as gates in physics, AND gate or gate not gate. Okay, but it's quite intuitive. And the OR symbol, which is this pipe symbol also, which is just below your backspace and just above your enter key on the keyboard. You'll have to use a shift to get that number, get that symbol. Then it means that either of the conditions should be true for the final condition to be true. Right? So when both of them are true, that's fine. When one of them is true, that's also fine. When both of them are false, then you get false. So, for example, this condition here, that is false, right? Because x is 20. This condition here, that is true. Because x is 20, so that's greater than 5. Now, what is line 256 and 257? What are they going to give me as the output?
Is it true?
Yes. So here what we are doing is we have false and true. And here we have false or true. So so can you say that again? I couldn't hear you all right. So which is going to give us true, which is going to give us false? Anybody?
One false.
First one is false. Yes, that's correct. Right? Because
True.
the second one is true. Okay. So this, it will just take you once to understand this, and then it's going to become quite simple. And the same thing is, the same comparison can be done on vectors also. So instead of x being a single value, you can have a vector. Now, so we've been seeing these examples, right? How x behaves when it's a single vector, so when it's a single element. So if I do y, let's say less than 12, so you see, it will give me, it will compare for each element. So 5 less than 12, that's true. 10 less than 12, that's also true. 15 less than 12, that's false. 20 less than 12, that's also false. Right? So now here, this line, it's false, false, true, true. And this one is true, 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 false. And now we are doing an and here. So it's going to compare this and this. So false and true, that's false. False and true, it's again false. True and true, that is going to give us true. But this true and false is again false. Right? So here only the third position is satisfied for both our conditions. Rest the three positions, they are returned as false. Okay. Likewise, when we are doing or here, so in all the cases, there is at least one true. So it gives us true for all of them. I would not be able to spend a lot of time on this right now, but again, you'll have these scripts. Go back and try to run them slowly. Think about what the answer is, and then see if that answer is what you get. Okay. Now, the double and the double or, they behave a little differently. Okay. So what you can see here is what happened here? Why did it give an error? Okay, I did not expect it was going to give me an error. I need to check this. Okay, anyway, this has been explained in the lecture. In case there's a question that needs your immediate, that immediately needs to be solved, then you can just refer back to the lecture in case I'm not able to solve this and send you the correct thing in time. But basically what the AND symbol is going to do is that it's going to calculate these things only up until you get the first true. I mean, it's going to give you till you get true values, and it stops when you get a false value. Okay. Anyway, I will get back to you on this one. Sorry, this was I missed the error earlier. Okay. Now just one another thing. We might use it in one of the later classes, but currently we have been accessing elements of a vector using the position, right? So if you want to access the second position, so we'll just write 2 here. But what we can also do is we can do something like this. So we can write as inside the position thing, we can write a vector made of trues and false, and we'll just write that the second vector has to be true. Everything else is false. So if I write that, I'm going to give 10. If I write this, then also I get 10. Okay. So again, this is, it might seem like a useless activity right now, but it comes very handy later. Okay, so we'll talk about this as and when need arises, but this is a very handy tool. Okay, I think the final thing for today is these matrices that we've made, we can actually save them in as a CSV file. So just one thing to remember is that R is not very fond of the Excel format. So the XLSX format, that's not very compatible with R, but a CSV format is great, right? So CSV stands for comma separated file, but you can easily open it in the Excel software, right? So whenever you have to write, so write means writing down a new file, whenever you're creating a new file, the function is going to be write.csv here. It's different, write.table and things like that, but we are focusing on write.csv. You have to write 2 arguments there. The first argument is the variable name. So in this case, that's M. And the second argument in double quotes is going to be your name of the file. including the extension. So that's important. Okay. So I'm saving the matrix, this M, and I'm calling it matrix m.csv. And if I press Control Enter, then it's going to get saved into the working directory. Remember we talked about the working directory. So now we'll just go to this folder, and it's this one. And now you can see this one's made. It just got made just now. So if I open this, it opens in Excel. And what you can see here is that the row names or the row indices also came along. So if I don't want that, I can just write row.names as false. And I've closed the file. And then if I run it again, then I can see it's created a new file. And now it looks a lot better. So column names are definitely something you would generally want, but row names are not always of interest. Sometimes they are, very often they're not. Okay. So again, close the file. If you want to make any changes, close the file, rewrite the file, and then open it. R cannot write a file while it's still open in Excel, right? Just like you can't rename a file while it's still open. Same thing. Okay.
Um, I I have a just quick question.
Yes.
Like when we are exporting this matrix, so can we export with the name? Like earlier we have learned like how we can name the row and column.
Mm-hmm.
So can we write together and export with the like name of
Yes,
column and
yes,
name of row?
yes. Yes. So if let's say we had named it here, right?
Yeah, in the
Where
beginning itself.
yes. So let's say this one. So
Yeah.
if you have named it like that, and then let's say I'm going to save it with a different name. So now I call it with names, something like that. Because I've overwritten the variable m. And if I save this, and then you see there's another matrix created. And oh, sorry. Yeah, I don't want this row name false thing.
Yeah.
So let me close this. And if I run this again, and then I open this, then yes, you've gotten your row names and call names.
Yeah. Thank you, ma'am.
Yeah. Okay. All right. Good questions. So yeah, questions like these are always welcome. So I will check what's happening with these here. I'll also check what the formula is, what the command is to calculate the adjoint of a matrix. And I think this was something that I also couldn't figure out. I'll see if I can manage the example eigenvector and eigenvalue.
Ma'am,
Okay.
actually, I don't know, in the last technique that you are mentioning, it's a eigenvalue having a 0. Oh, sorry, -1. If we add them, so -1 could be a common here, or maybe 0. That's a no, that's a PPT one. This one, because if we are adding this become -1 and this also become -1. So if we take a -1 common, then it become 1. So
Yes.
-1 will be our eigenvector.
No. That's not how it works. So you should get your vector again. So it should be vector multiplied by a scalar. So the same vector should come on left and the right side. So you should have 0, 1 on both sides. I think I'm just making a very small calculation, something. Let me figure it out after the class, and I'll share the PPT with the correct calculation by tomorrow. So I do have a few questions here. I think they're just 4 or 5 questions, so I think we have enough time to get those. So, okay. So which of the following is the correct outcome of the command row means for the matrix constituted by this command? So again, we're not going to do a lot of calculations. The first thing is you write the matrix down. So it's going to be, so it's by row is false. So we fill it by column, 61, 62, 63, 64, 65, 66, 67, 68, 69. and then you need to find out the row means. So row means is means of each row. So this is going to be, I think, this one, right? This should be the mean. Yeah.
Yes.
Okay. What will be the output of the command x is equal to diag 5 row 3 col 8? So this we have sort of already seen, right? We have 3 rows and 8 columns. So how many diagonals are we going to have? How many diagonal elements are we going to have for this matrix?
3, 5, 5, 5.
3.
Yeah.
3. Yes. So 3 diagonal elements, all of them are going to be 5, 5. Correct. So it's going to look like, it's going to look something like this, a 3 by 8 matrix, and your diagonal elements are going to be like that, right? And everything else is going to be full with zeros. Okay. Which of the following is the correct command to obtain the multiplication of the two matrices? And okay, it asks you to give the correct answer also, but for now you can just tell me which of the commands is will you use to do a multiplication of two matrices? Not element wise, but multiplication.
C.
Yes, correct. Okay. Oh, that's all. That's all the questions I had. Okay, because we discussed a lot of them while we were revising the commands themselves. If you have any confusion from assignment 3, then we can go to that. Otherwise, this is the end of this week's class. And the assignment is definitely scheduled for next Wednesday. And our next session will be on Friday. But anyway, we will have another session on the coming Tuesday as well, taken by the other TA. So if any of you still have any doubts, you can join that session to ask. Or you can put it in the discussion forum. Okay? All right. So that's all. I'll stop sharing the screen. And thank you so much.
Sure.
All right. Bye-bye. Good night, everybody.